So let me go through another example where the dimension is 3. So since I haven't drawn that three-dimensional column vector space, I've sketched it here. It's just a sample vector that usually we use this rectangular box to visualize it as a three-dimensional situation. So here's a typical vector there. This time it's going to have the three coordinates C1 and C2 and C3. And if you have three numbers, there's a unique location in this three-dimensional space. Not only we're looking at it's a collection of positions here like this, but we're actually looking at a column vector, so that arithmetic and scalar multiplication, and we have that much of arithmetic built in. Okay, our problem is that looking at third-order homogeneous equation, and the L is the associated operator, and we're looking at kernel of that operator, the space of all solutions of that third-order equation. And each function in here has its three values. Its function value is C1, is the first derivative, it's called C2, and its second derivative value is C3. If you pick a function in that kernel, solution of an homogeneous equation, they have always these three values, and they correspond to this column vector over in here. And if I have this arbitrary column vector, there will be a function over here that has this three value, which is the existence and uniqueness theorem. So there's correspondence in this picture. Again, and there is this y1 and y2, y3. I hope you remember what those special functions that we talked about in this three-dimensional space in here, but that's not always something that's available to us. So whatever three things that's available to us, as long as they're linearly independent in this three-dimensional space, then you can use those three things instead of these special ones to generate everything. So for example, if I have linearly independent three column vectors in three-dimensional space like this, and all the vectors inside, here is the scalar multiple linear combination of these three vectors. So that goes to that part in here, have the same statement. So I'm going to write down corresponding function here, f1 and f2 and f3 there. By existence and uniqueness, and if you have these three vectors, and there will be these three functions. So we're going to go ahead and find f1, f2, f3 of some example, and look at these three column vectors and understand they're linearly independent in here. And then come back here and write down all the solutions with the C1, F1, C2, F2, and C3, F3, and stuff like that. So let's look at the example. Now, with this picture, these three-dimensional space, column vector, and space of function, these two connection gives us a great tool to determine, or power, or gadget to determine linear independence of the three vectors that are coming from the solutions of homogeneous equation like this. So that kind of does it in a practical method. But also in the standard textbook, this linear independence is discussed through something called Wronskian. And statements are sometimes presented in a confusing way, so I'm going to give you a very clear statement, and whether it's not confusing. But in practice, and if you have three functions are coming from the homogeneous equations like this method is very, very efficient, but you can also use this Wronskian method as well. So first, let's review the definition. I'm just doing this for three functions, but I hope you see the pattern so that you can extend it to three or higher, or even to two functions. So another thing is that these three functions are not necessarily coming from the solutions of a homogeneous equation. Just arbitrary three functions, we can consider something called Wronskian, which is defined and denoted like this: W of f1, f2, f3. If you have three functions, we'll consider this 3 by 3 matrix. The first row is the function, and the second row is the derivatives of the three given functions, and the third row is the second derivative. And if you have 4 functions, we're going to consider 4 by 4 like this. So remark that to make sure that you understand, remark here, this Wronskian W of 3 functions is a function. So if you have x value plug in, then it's going to be changing. So there's an input value. So that's the name of a function, is a function. Not a number that we looked at in earlier example. So this is a function. So here's a theorem about this Wronskian. Suppose these 3 functions, f1, f2, f3, whether they're solutions of a differential equation or not, if they're dependent, then we can conclude that Wronskian of these 3 functions are identically 0. This 3 bar means no matter what x you plug in here, turns out it's always 0. So that's one statement. The second statement is about the situation where the 3 functions are independent from each other, and we don't have a conclusion about the Wronskian. We need additional condition that all these fk's are solution of homogeneous equations. An easy way to write it is that they're coming from the kernel of, in this case, a third order linear differential equation. If we have this additional condition, we have a conclusion that Wronskian is not just not identically 0, we have a stronger condition. The values of the Wronskian will never 0 for any value of x that we are considering, any x in that value. So that's a stronger statement. Where it's not that identically 0 or not identically 0. In this case, is stronger. It actually never hits 0. So this is the statement. From there, we have a contrapositive statement. So if we have the values of the Wronskian in here, and we can conclude about dependence and independence. So that's where it actually uses Wronskian in the context of the differential equations. So the contrapositive statement goes like this. If Wronskian you calculated is identically 0, then of course we want to conclude that the function we're looking at, this f1, f2, f3, are dependent. That's what we wanted to conclude. But just from the logic here, and it is not sufficient, and we will discuss an example that this is not true. So what we have to do, we have to add one more condition, so there are solutions. These fk's that we're looking at is actually solution of a homogeneous equation. It's coming from the kernel. If we have this additional condition in there, then we can add, we can conclude the dependency. Since we're looking at these problems in the context of differential equation, this is a pretty good statement. And the second condition there is doesn't have to be this strong statement. Either Wronskian is going to be identically 0 or not identically 0. Sometimes it's 0, sometimes doesn't hit 0. If you have this much of a condition without knowing that the functions are coming from the solution, we can still conclude that these 3 functions are linearly independent. So that follows immediately from the theorem here, is immediate corollary. So let us first prove this corollary. There is a proof of this corollary 1 here. This is called a proof by contradiction. If we have these 2 conditions, either this function is dependent or independent, that's the only possibility. And so we suppose it is the other case. Suppose they're linearly independent. But we have this condition. This Wronskian is identically 0. There are solutions. So what we have from the theorem is that we have this condition here matched. We are in the solutions. And we assume that it's actually the independent. This part is not changing, but this part is what we are hypothetically assuming. So that's part fixed. But as long as we have this independence condition and kick it in here, then we have this statement falls out. The Wronskian will hit non-zero value for whatever you plug in here. In particular, there is some value. So from the theorem item 2 implies that in particular, the Wronskian value x is not 0. We don't need that strong statement. For some x, whatever you choose, is going to be non-zero. That violates, contradicts the condition that we haven't used here. The Wronskian is identically 0 no matter what you plug in here, i.e., it follows that that x we're looking at must be 0 no matter what you plug in here 0. This is contradictory, so this can't happen. Now let's consider the proof of the corollary 2 here. Wronskian is not identically 0, then we have to conclude its independence. Like we did it before, we assume actually this f1, f2, f3 are dependent, like that. Suppose we have a dependence and we have the still conditions. Wronskian is not identically 0, but it happened that these functions are dependent. Can this happen? What we have in this theorem about the dependency is this part here. It's as long as the functions are dependent, this is the condition we have, it must be, whether it's a solutions or not, it's identically 0, but it contradicts is not identically 0. So we have the theorem 1 implies, because of this hypothetical situation we are imposing it in here, says this Wronskian must be identically 0, but we started with the Wronskian that's not identically 0. So that's a contradiction. That's a contradiction here. So this can't not happen in any circumstances. So that proves this corollary. So this is what we use actually. We have 3 functions, compute the Wronskian, look at it as a functions identical as 0, sometimes it's 0 but sometimes not, then we can conclude it's a dependence and a linear independency like this. Let's now consider the proof of the first case here. If these things are dependent, the Wronskian is going to be 0. So dependent by its definition, and there are constants. Alright, in this video sequence I haven't really formally defined what the dependence and independence are. In 3-dimensional situations, it means in the linear algebra language, dependence means that we can look at this 3 vector and there's some linear combination such that some of the coefficient is non-zero, but we can still get this thing identically 0. The meaning of this one is usually that one of the function, where if this is C1, that one in here, one of this function can be isolated. If this is non-zero, you can divide it. One of the function is generated by the other 2. So that's the equivalent condition of being dependent. We're looking at the 3 functions. One of the function here is actually a linear combination of the other 2. Then we will have this type of condition. And this is as a function is identically 0. Now, Wronskian requires the statement about the derivative, so we can pass, because these are identically 0, it's not the equation, it's the identity. We can have derivative statement like this. Since c's are constant, if you differentiate at one time, this of course remains as a 0 function, and you can continue differentiating, and we will stop here. That's what this up to the second derivative is what Wronskian is concerning. So we have this statement. Key thing is that we can look at this as a system of linear equation with the C1 and C2 and C3 as a variable. So if you write it here as a matrix form, F1 is a function and F2 and F3. So if you look at this matrix in here, and C1 and C2, C3 are multiplied there, so this is the definition of the matrix multiplication like this. And it is equal to, here is a 0 vector, so it's a 0, 0, 0. Right? This is not Wronskian, this is just a matrix, but this matrix has all the x's in it, so you have to look at this matrix that it's changing as a function of x, while the C1 and C2, C3 is a constant. As x changes, this guy doesn't change. And one of the CK's here, non-zero. It is the fact from the linear algebra that if this equation called homogeneous equation in linear algebra that has this 0, 0 in here, if this one has a non-zero solution, is not 0, 0, 0, of course makes everything 0 in here, but if there's a non-zero entries here making 0, it is the statement that we have the determinant of that matrix there, mx, which is the Wronskian, we have it here, is 0 all the time, no matter what x is, because this doesn't depend on x in there. That's why this is identically 0. If this changes with x equals 0, then this is not identically 0, but this is fixed no matter what x you put it in there. The determinant of this matrix, whose entries are numbers after you plug in x in there, that has to be 0. That's in linear algebra, and this constant is always there no matter what x you plug it in there. So that must be identically 0. So that proves the first statement. So let us prove second statement there. Sorry about that. All right, back. The conclusion we wanted to make in here is this Wronskian and never hits a 0. So this is another one with a proof by contradiction. So we're going to suppose this Wronskian is actually hit some 0 for some, not all of them, for some special alpha in there. Suppose there is a single value of alpha we discovered such that Wronskian became a 0. And what happened with these two conditions? What can we conclude in something, contradiction, something? So that's what we're going to do. So the Wronskian with x value, so we're going to turn that matrix into a matrix of a number entry, not function entry. Right, here's that matrix again, and it was the matrix with the function entry. Now if you plug in this special value that was hypothetical existence, and with that value, and we plug it in here, and we get a matrix of 3 by 3 with a number entry in there. But from here, we assume the Wronskian there is a 0, so that means the determinant of this matrix, m alpha, is 0 for that special value, not identically 0 for that special value is 0. So what we can conclude here is that if the determinant of this 3 by 3 matrix has a determinant is 0, then there is a column vector C1, C2, C3 with some ck non-zero, whatever that is, all of them matter, and there is this 3 values of c's, that is one of them non-zero, such that this matrix M alpha times this column vector C1, C2, C3 is still 0. Right? If this happened with some non-zero entry, we conclude the determinant is 0, but determinant 0, we also conclude that there is the existence of non-zero 3 values. So let me emphasize it again. All we know is the sum ck are non-zero. So I want you to think about expanded version of this one. If you actually multiply out C1 and C2 and C3 and here, you will get top row that looks like this: C1 F plus C2 F2 and C3 F3. With alpha and alpha and alpha in there. That's going to be the top entry as you multiply the C1 and C2, C3. And in the second entry, we have the similar statement with the primes in it and everything. Okay? So that's how these two things compares. But what we're going to do in here is that we're going to define the new function zx. No alpha is in there. Zx like this. F1x there, F2x there, and F3x there. So this is a function z with these 3 coefficients in front of it. And to make an analogous statement for the second and third row, we're going to differentiate the z prime vex. We differentiate it here. We get this statement: these C1 and C2 and C3 are constants. So the functions are differentiated. So z double prime. So second derivative of z is going to look like this. We have a statement about these things when x is alpha. because alpha is plugged in here. So think about it again. C1 and C2 and C3 are multiplied in here and there and over there. And all of the things is supposed to be 0. So what we have about this statement is that if you plug in x equals alpha in there, the top row, it's supposed to be 0 there. So this, with x equals alpha, this top row becomes 0. With x equals alpha in there multiplied by this C1, C2, and C3, that will be exactly z prime of alpha. So that whole thing is supposed to be 0 as well. And z double prime of alpha, third entry after you multiply this column vector to this matrix, also 0, so we have this thing in here. So if you look at this, especially consider this function gx, this function has this special condition that z of alpha is 0, z prime of alpha is 0, and z double prime of alpha equals 0. Another fact that I'm going to add in here, and with which you can apply the existence uniqueness theorem, which is that this function I consider the z here is still in the kernel. It is a solution to the homogeneous equation. Why is that? Because it's part of the condition that individual function f1, f2, f3 are from the equation, from the kernel. These are solutions of the homogeneous equations. That's why this combination that we considered is still inside the kernel. So we use that condition. Now, think about uniqueness and existence. And if you're looking at some solutions of this linear equation where the initial conditions are 0 and 0 and 0 like this, and of course the 0 identically 0 function does satisfy all this condition, and by existence and uniqueness it says this function is actually identically 0. Alright, I was running out of room, so I made it really small, but I hope you can see everything here. These are the derivative value, and then we found that, conclude that by using the existence and uniqueness, the zx is identically 0. So let me write down what the zx is. C1 f1, C2 f2, and C3 f3 is this function's identically 0, and sum of the ck there is non-zero. So if I write this one down on here, that's the conclusion. This is what we have so far from the supposition that there is this value alpha that makes Wronskian 0, and some ck non-zero came from the determinant 0 condition. So here I'm showing you the condition here again. We use this Wronskian equals 0, which is the opposite of the conclusion, and at some point we use this, the functions are coming from the kernel. That's something we used, but this is something we haven't used yet, f1, f2, f3, linearly independent. So if you look at this statement down there, it doesn't seem like it's linearly independent. If it's linearly independent, and only possibility of this linear combination being identically 0 is all coefficients are 0. That's the opposite statement of dependent. But here, this Wronskian becoming 0 gives us the existence of number. So that makes this linear combination identically 0, and is one of the conditions is coefficient is non-zero. That is a dependence condition, right? It means it's dependent. So that contradicts the independence condition we have it there. So there is a contradiction. Therefore, the existence of a single alpha value that makes Wronskian 0, the supposition is necessarily incorrect. So that proves the statement is no matter what you plug in, it's going to remain non-zero.